Welcome viewers to the 13th lecture of our series of spur and helical gear cutting. So, today we are well poised to start some discussions on gear shaping machines. So, basically we will discuss about gear shaping machines and take up a numerical problem, and I will also post some supplementary material in which you can see actually a gear shaping machine in action, and we will also solve some multiple choice questions. Okay. So, let us start with this drawing. Though at first sight this might be looking quite formidable, actually the thing is quite simple. In what way? For example, in all such drawings involving a large number of machine elements, let us first pinpoint or identify the prime mover. This is the prime mover, the motor. The motor is rotating at say 1400 rpm, and after that we have some regular machine parts. For example, let us see from here, we have a gearbox here, and from our prior knowledge we can say that this must be the speed gearbox. So, here it is written speed gearbox UV. So, inside there are some gears. You might say, what are the values, what are the numbers of teeth of these gears? I will say it will vary from case to case. If you are applying a particular condition that I want this particular cutting speed or this particular number of strokes per minute, that will decide this particular gearbox setting. So, at this moment it is having no particular numbers of teeth assigned to these respective gears. After that, at the output side of the gear box UV, I have this particular machine element connected with a disc shaped body. What is this? This one looks like a threaded element. Okay, this is a threaded element, and this value of K1 equal to 2 and Z1 equal to 20, this gives you the hint that it must be a worm and worm gear pair. So, we have a worm and worm gear pair just beyond the speed gearbox. Okay. That is fine. What does this worm and worm gear pair do? It is having number of starts equal to 2 and number of teeth on the worm is worm gear, it is equal to 20. Which is the worm gear? This is the worm gear. Okay. This one is the worm gear. So, it will undergo rotation. Coaxial with the worm gear, we have a sort of pinion, or sorry, not a pinion, we have a pulley attached. Okay. This one is a pulley and it has the same rotations per minute as that of the worm gear. With this pulley we have a belt, and this belt is going all around a larger pulley at this particular position. So, we will effectively have rotation of this larger pulley due to this belt connection with the smaller pulley. Once this pulley is rotating, there is a connecting rod connected with a a reciprocating block. Okay. This one, this slider, okay, this slider slides in these guideways to and fro, and as you can well understand, this rotation causes reciprocation of this block. Once this is reciprocating, this shaft with an end collar, okay, embedded inside this block will have to move up and down. So, this one also moves up and down, and it is a splined shaft. What is a splined shaft? A splined shaft is that which has just like gears, it has teeth cut on it. Okay, in its cross section you will find, just like gears, you will have some teeth. What is the purpose? The purpose of the spline shaft is that while it is moving up and down, it can also suffer rotation by a member connected with it, teeth on teeth. We will see an example both as a drawing and also as an active, working member in a video recording of the process. So, we have come down up till this point: pulley, connecting rod. So, this pulley, this arm is acting as a crank. So, crank, connecting rod, sliding block, okay, and then spline shaft. At this moment, the spline shaft has not been given any rotation. It's simply moving to and fro. It's reciprocating. This reciprocation, at the end of the reciprocation, we have the cutter. The cutter is represented by a trapezium. But up till now, you have noticed that we have referred to the cutter as just another gear, a perfectly made gear. Then why does it have this trapezoidal shape? At least if it had been, circular in shape, that is, if it had been represented by a perfect cylinder, it should have come out as a rectangle, just like the workpiece with an axis line. But we actually give some relief angle or clearance angle towards the back of the cutter, so that while it's machining, its surface does not, this surface does not interfere with the finished surface formed on the workpiece. As it goes down, it removes material by this side, the rake surface, and the clearance surface is relieved away. Okay, this surface is relieved away, the flank of the cutting teeth, that is relieved away from the finished surface, so that there is no unnecessary rubbing. So, we are now convinced that the cutter is capable of moving up and down due to all these, belts, pulleys, gearings, bearings, all these things ultimately make the cutter move up and down. What are the other connections? Let us have a quick look at that. Coaxial with the larger pulley, if you look at the top, we are having a gear. This gear is connected with a number of gears and it makes up a gearbox, though not exactly shown in a proper rectangular, proper box. This serves as the feed gearbox. So, we basically have a bifurcation here. So, just after the speed gearbox, there is a bifurcation. One side goes for reciprocating the cutter, okay, up down, and the other side goes, and ultimately this one connects up with a bevel gear. Okay, there is a bevel gear pair which makes ultimately this shaft rotate, this vertical shaft, long vertical shaft. What's it doing? It's having another bifurcation. Power flows out here and the power flows out here in the form of rotations. And let's take this one. So, through this particular bevel gear pair, we are having rotation of this shaft. And now you are well conversant with this shape. This must be another worm and a worm gear. What's this worm gear doing? Exactly as we previously came across, it's making the splined shaft rotate. But when the cutter shaft is moving up and down, how come this is remaining in position and not moving up and down with it? That's it, because the spline shaft can move through bodies without sharing its straight line motion. But when the spline shaft is rotating, it has to share its rotational motion with another member which is connected to the spline shaft through teeth. So, RPM is shared, rotation is shared between this worm gear, this one designated as Z2 equal to 50. That means it has 50 teeth and the number of starts on this worm is equal to 1, and therefore, they rotate together. Rather, the worm gear makes the cutter shaft rotate. Now, why doesn't the cutter shaft come out of assembly here? Because it's still inside a rotational space, okay, So, it is it's within a surface of revolution, hollow surface of revolution. So, there is no problem. It remains in position, moves up and down, and also rotates inside this embedded space. So, now we have rotation of the cutter added to its reciprocation. So, as previously planned, the cutter is now reciprocating as well as rotating. This rotation is brought further down and we have the index gearbox. So, up till now we have come across the speed gearbox, we have come across the feed gearbox, and we have the index gearbox here. The index gearbox has its output given to yet another worm and worm gear pair, where number of starts is equal to 1 and number of teeth equal to 60. That is good. So, where do we arrive? We arrive at the workpiece. If you remember, the workpiece has rotation as well as a radial in feed towards the cutter. We have not studied the radial in feed as an added line of mechanisms bringing the ultimate motion to the workpiece towards the cutter, but we will definitely study this thing, at least while watching a video on the machine. We will definitely come across this radial in feed. So, this rotation ultimately rotates the workpiece, because if you remember, in the gear shaping and the gear hobbing machines which work on generation, we have to make the cutter and the workpiece rotate individually, by giving power to them. It is not that one of them drives the other, because of the simple reason that the workpiece to start with does not have any teeth on it. So, it has to be made to rotate. The cutter and the workpiece both have to be made to rotate as if they are rolling against each other as fully made gears. So, that is what we have done. We have made the cutter rotate, we are making the workpiece rotate here, and we will maintain the RPM ratio as if the workpiece is already having the required number of teeth. The cutter has a fixed number of teeth, this particular cutter, if you do not change it. So, now we are convinced that the single motor source through these 3 gearboxes and some other mechanisms which we have discussed now, it is able to successfully reciprocate the cutter, rotate the cutter as well as rotate the workpiece. And now it is a good time to solve a problem and see what sort of restrictions and other things define ultimately the gearbox ratios. Question. The question is, I am cutting a gear of module 2 with 40 teeth. So, module is 2, 40 teeth, and what I have not what I have forgotten to mention is that the gear to be cut is a straight spur gear, not a helical gear. So, a straight spur gear is being cut with module 2 and 40 teeth. So, the cutter has 20 teeth, that is good. The cutter has 20 teeth. The machine should be set up for 98 full strokes per minute. What does that mean? It means that there will be 98 up and down movements of the cutter per minute. Fine. Now, how do we do this? I have already provided you with the answer, so that you can try it out yourselves before we discuss the solution and see whether you have the correct answer. So, the correct answer is UV should be 14 by 15. Next question is, I want a circumferential feed of 0.25 millimeters per full stroke of the cutter. How do I achieve this? The answer is that US, the feed gearbox, should be set to a value of roughly 1 by 10. So, if you set a value of 1 by 10 to the feed gearbox, you will be achieving a circumferential feed of 0.25 millimeters per full stroke of the cutter. Now, you might ask a question here, that if I have 0.25 millimeters of circumferential feed on the workpiece? Will it be the same thing? The answer is yes, because when the cutter and the workpiece, they are rolling against each other without slip, they are supposed to have the same amount of circumferential movement. Okay? They share equal circumferential movement. Therefore, we can either say that circumferential feed on the cutter of 0.25 millimeters or circumferential feed on the workpiece of 0.25 millimeters per full stroke. Last of all, how do I set the value of UI? The answer is UI is defined by the number of teeth which is being cut, okay, number of teeth which is being cut and the cutter number of teeth. Okay. So, from that UI, the solution is UI for this particular case will come out to be 3 by 5. Okay. So, if you are interested, solve the problem yourselves and compare the answers when we compare the answers with these answers which are provided, and if you have any issues, then we can share the solution and you can quickly look up what might have gone wrong, or maybe you are right and this discussion has some issues. Okay. So, let us quickly go through, and here we are having some symbols which I have discussed in case you have you have some doubts about some of the mechanisms. This is a worm and worm gear, this is the worm, this is the worm gear. There are other ways in which we have depicted it. This is a pair of bevel gears and this one is a worm gear with splines inside which is fitting to this splined shaft. Okay. So, worm gear on a splined shaft. So, the four main motions, how is the cutter reciprocating? Already discussed. How is the cutter rotating? Already discussed. What is the interconnection? The splined shaft part, already discussed. How is the workpiece rotating? We have already discussed this. How is the workpiece translating, which means the radial in feed? This we have discussed theoretically, but with respect to a numerical problem, we will definitely take this up. This is an example how the splined shaft works. Suppose you are seeing from the end one splined shaft here. Splined shaft is rotating, and this is a member, a hypothetical, a virtual member, which is a machine element with a hollow interior with fitting splined teeth. So, these teeth match exactly with these external teeth. So, these are internally cut teeth in this hollow member, these are external teeth. So, that if they are assembled, they will have the same rotations per minute this way. Okay. Inside there is the splined shaft and outside there is this member, and as we discussed, they have they have translational independence. While this member might be translating, the splined shaft might not. Now, the solutions. If we start from, I think we will try it out on pen and paper. Let us see. Yeah, keeping this one, let us try on pen and paper the solution for UV. Starting from the motor, if you look at this paper, okay, starting from the motor, we have 1400 RPM. Actually, it should have been 1440, but anyway, it does not matter for the sake of calculations. To understand the principles, it is as good as 1440. So, we start with 1400 RPM, and then comes the speed gearbox. So, we put UV multiplied by, so once you multiply this, since UV is equal to output RPM by input RPM, this is the output RPM of the speed gearbox. So, we will write output RPM of speed gear box. All right. So, if this is the output RPM, it must be shared with this particular worm. So, the worm has this RPM, and therefore, just multiply the speed ratio of the worm and worm gear, which is equal to K1 by Z1. So, we come to the output side of the worm and worm gear, which means the worm gear RPM. The worm gear RPM is shared with the pulley. So, if the pulley speed ratio is given, this is the pulley RPM. So, we can write pulley, small pulley RPM, also the worm RPM equal to worm gear RPM. That is good. So, once we pass through the worm and belt pulley, therefore, if you notice in the figure, it is written pulleys speed ratio 3/4, and everywhere we will assume that the speed ratio is given as output by input. So, that we can simply multiply this 3/4. Okay. So, now we come to the crank. The crank RPM is this. So, we write crank RPM, and this essentially is equal to the number of strokes, equal to number of strokes per minute. So, we have found out the number of strokes per minute, and we equate this to the number of strokes which is required, and it said 98 should be the number of strokes per minute. That is it. Now, we can solve for uv, but K1 by Z1 is in variable form. So, we have to replace this by its value. So, selecting a fresh sheet of paper, we write down 1400 multiplied by uv multiplied by K1 by Z1 is 2/20 multiplied by 3/4 is equal to 98. Once we have this, let us solve for uv. uv comes out to be, let us see, a lot of cancellations perhaps. Yes, 0, 0, 2, 2, and 144 will definitely cancel with it. So, we have 12, 3 and 2, so 5. So, uv ultimately comes out to be 98 divided by 3 and divided by 35. I think 7 will cancel, so that we have a 5 here, and what do we have here? 1, 2, 4, 14. So, it comes out to be 14/15. So, answer is uv equal to 14/15. That is it. This is the answer. All right. So, let us take the next case. I think we are now on the second problem. I want a circumferential feed of 0.25 millimeters per full stroke of the cutter. Okay. Now, in this case, if you look at the figure, okay, we are starting from the cutter. So, for one stroke, we will start moving from the cutter, move backwards, come to the main line, then move forwards and go to the rotation of the cutter and equate the circumferential movement to 0.25 millimeters. Okay. So, let us do that. So, let us start from cutter reciprocation. cutter reciprocates once fully, 1, 2, up, down. Therefore, the large pulley, the large pulley rotates once fully during this time. Okay. So, this one rotates once, and therefore, we can say the input to the feed gearbox is only one rotation. So, once we give one rotation to the feed gearbox, it outputs US number of rotations, and this passes through this one, passes through this worm and worm gear, and ultimately rotates this particular gear. Let us find it out. First of all, one reciprocation of the cutter equal to one rotation of the large pulley. So, we write large pulley. We are talking about rotations, that is good. This one will, when multiplied, so this is input to the gearbox US, feed gearbox. So, the output of the feed gearbox must be equal to 1 into US. This is always expressed as output by input. So, multiplied by input, only output remains. Output to the, so we will write output of US. That is it. So, after that, after US, we pass through the bevel gear pair. So, we multiply 1 by 1, 1 is to 1. That actually, there is no need of doing that. Anyway, to keep track of the mechanisms which we go through, another 1 is to 1 will be there, and after that we pass through the worm and worm gear. In what way? K2 equal to 1, K2 by Z2, and therefore, we are now on the cutter shaft in the form of rotations. So, we can write rotation of cutter shaft. However, cutter shaft rotation is not specified in any manner, but cutter circumferential movement is specified. So, let us find out for these many rotations how much is the cutter circumferential movement. What is the cutter circumferential movement for one rotation of the cutter? Definitely pi d, that means one full circumference. That is, if the cutter is here, or rather let us draw it in an isometric form. Yeah. If the cutter is here, if this rotates once completely, how much is the circumferential movement of the cutter? Definitely equal to one circumference. Therefore, if you have x number of rotations of the cutter, this we know, rotation of cutter shaft. So, the amount of circumferential movement on the pitch circle must be simply equal to pi d, this thing into pi d. One rotation, pi d amount of circumferential movement, x rotation, x into pi d. So, this multiplied by pi d, where dp is the cutter pitch diameter. Now, this can be simplified. So, we write that this finally equal to cutter circumferential, oh my god, there is hardly any space there, cutter let us climb down, circumferential, I hope I am making no spelling mistakes, cutter circumferential movement for one stroke. Okay. So, let us now just sum it up and find out how much it is. 1 into US into K2 by Z2, let us see what is K2 by Z2, 1 by 50 multiplied by pi into DPC. What is DPC? The cutter pitch diameter, that must be equal to, this is a case of a spur gear, that must be equal to m into z. So, m has been given to be m into z. Z means cutter number of teeth, equal to, this must be equal to 0.25. This circumferential movement must be equal to 0.25 millimeters, and for that we will solve for US. So, once again, all this thing is the rotation of the cutter for one stroke, and I multiply the circumference, I get the circumferential movement, and I equate it to 0.25 millimeters, which is the circumferential movement of the cutter. Having understood this, I quickly find out what is US. By the way, let me just put in this value, so that we have the final form US into 1 by 50 into pi into m. What is m? 2 given. Number of teeth on the cutter 20 equal to 0.25 millimeters, which is what you call it, given. So, US is solved as 0.25, let us put in 1/4 into 2 into 20, and down goes pi, up goes 50, and this one as a solution, let us see how much it is, 0 and 0 will cancel, 2 will not cancel, sorry. So, this will be 5 by, how much is this, 8, 2 2s are 4, 16, 5 by 16 pi. Have we made any mistake? Let me quickly check. Yeah, hopefully this is correct. I will just compare this with the calculation which we have already done and see whether we have got something correctly. So, yeah, US into 1 by 50 into pi into 2 into 20 is equal to 0.25, and hence I think we have solved it and got a particular value. So, I do not have a calculator just with me at this moment. So, you can quickly calculate it, whether it comes out to be 1 by 10 roughly, that is 0.0999 recurring. So, it is being made to be equal to 0.1, that is it, 1 by 10. So, if you put in this particular feed gearbox value, you will get a circumferential feed of 0.25 millimeters. So, with this we come to the end of this lecture. We will take up the rest part of the problem in the subsequent lecture. Thank you very much.